Hello everyone. This paper is about rewriting query on SPARQL views. It is a joint work by Florida State University and IBM Research and HP Lab, China. So the talk will be organized as follows. I will briefly introduce the problem and outline the solution. And after that, I will give the detail of the solution and present the main results and point out its limitations. And after that, I will bring up optimization and show some experimental results. After that, then we can conclude. So answering query using virtual views is a classical problem in relational databases and can be encountered in many settings, including access control and data integration. A typical scenario is when a database administrator, a DBA, wants to enforce security clearance using views. So there are two cases. The first case is when the view is materialized. So suppose we have a database D and the DBA define and publish the hard copy of the database and grant the database to the users based on their access privilege. And user queries directly be evaluated on the hard copy of the database. The advantage of this solution is that the deployment of the solution and the query evaluation is simple, but it could have a problem if the database D is under heavy update. So we also have a space issue. So the second solution is when the views are virtual. So instead of publish the hard copy of the view, the DBA publish the definition of view and user construct their query based on the definition of view. And in the background, this query, for example, in this case, the user query Q is rewritten into the query Q prime and Q double prime. And in addition to that, in an access control scenario, the typical DBA will guarantee that the rewriting query is equivalent to the original query in terms of query results. The advantage of this solution is that maintenance of the database, original database, is efficient in terms of accuracy and consistency of the result. And on the other hand, rewriting query in relational algebra is known to be heavy hard. So the problem we are going to tackle in this paper is as follows. Answering query using views is a well-studied problem for relational database, but not well installed in semantic web description framework, which is RDF, and its query language, SPARQL. I'll briefly introduce these two shortly. So given a set of view definitions, V1 to VL on an RDF graph G and a SPARQL query Q over this set of view, so the goal is to compute a SPARQL rewriting query Q prime such that we guarantee Q prime evaluated on the graph on the original data G is equivalent to the original query Q evaluated on the set of views. So we consider two criteria in terms of correctness of the result. The first one is soundness. Soundness basically guarantee that the rewriting query, the result from evaluating the rewriting query Q prime on the base data G is containing the result from evaluating the original query Q on the set of views. And the second criteria is completeness. Completeness basically guarantee that the result from evaluating the original query Q on the set of views is covered by the result from evaluating the rewriting query on the set of on the original database. So basically, soundness and completeness guarantee that these two queries are equivalent. The rewriting and the original query are equivalent in terms of query results. Basically, soundness guarantee that the result from rewriting query is covered by the result from evaluating the original query on the set of views. Basically, it says that your rewriting query is not accessing anything that is not supposed to return by the original query. And the second criteria will basically guarantee that the rewriting query will cover all the results from evaluating the original query. So here's the RDF data. Resource description framework, RDF is common use in semantic web for knowledge representation. For example, here's a snapshot from DBpedia, one of the largest RDF data repository on the web. It basically describes 3.5 million things around our life and extract unstructured information from Wikipedia, Warner, and other sources and publish them in a queryable structure format, which we call RDF. The unit of RDF data is a link triple. For example, here, the subject predicate, an object describer, Alan Turing is born in year 1912. So we are interested in a SPARQL query of the following form. So a query is defined as a select or construct a result description followed by the where cost GP as a graph pattern. And it basically tells given RDF graph G and a graph pattern GP, the SPARQL query searches for subgraphs in G that match the pattern, the graph pattern GP. RD is a result description. There are two forms. For selection, it's basically project the results, projects the values of the variable in the graph pattern. It's just MySQL. For construct, it's a set of triple templates that construct a new RDF graph from the matches graph in G. I'll have some example for this construct later. Finally, there's a Boolean SPARQL query of the form ask a graph pattern, basically indicate if the graph pattern GP exists or not in the base data G. Here's a running example. Suppose here's a fragment of Eric's social network. Basically, it captures Eric's friend, direct friend, Amy again, and his friend of friend, him, and also his relative, Jim, and his relative or relative, Dan, and the cities these people are living in. In SPARQL, views are defined by construct, and suppose Eric wants to hide his relative or friend, P1, and his friend of relative is not in this picture. And hide any distinction between friend of friend, and hide any distinction between his relative or relative and relative. So he can construct 4 views, with each view reflecting part of this his social network. So one thing I want to mention is that the variable is defined with question mark and followed by the name of the variable. So suppose we have a query. Okay, one thing I forgot to mention is that he used v friend and v related to hide the distinction between friend and his direct friend and his indirect friend and his relative and his relative or relative. So suppose we have a query asking Eric's v friend and v relative who is also living in the same city. So how do we rewrite this query? So first thing we know that is that use a constructed query based on the vocabulary using reflect in the head of the view. But we need to rewrite this query since these views are virtual and only the where costs are assessing the base data in the database. So one thing we know that is the v friend using the query can match to the v friend in the first view, and it can also match to the v friend in the second view. In addition to that, we need to unify the variable using the query and the view. And we also need to push down this variable mapping to the where cost, since where cost is assessing the base data. So there are 2 copies of v friend and 2 copies of v relate, and 4 copies of for each of the v lives we have 4 copies. So together there could be an exponential blow up in the output. So here are some details of the algorithm. And suppose we use the examples in the previous slides. And the way we do the rewriting is we divide and conquer. We first build a rewriting for each query statement, and then we massage them together in a meaningful way. So the first thing we do is that we build a candidate view for each query statement. Candidate view is nothing but a set of buckets telling how to rewrite or exhaustive how to rewrite this query statement. So, for example, we can use the first view since v friend appear in the first view. We can use v friend in the first view to rewrite v friend in the first statement. A bucket basically recall which view we use to rewrite this query statement, and we also need to recall how to change the variable names. For example, here I need to push down the variable from the query to the view. We need to change the f0 to be p in the view, to be p in the query, and f1 to be f5. And alternatively, we can use the second view to rewrite the first statement in the query. So we do this so and so forth for each query statement, and we build a candidate view for each query statement. And after that, we can rewrite this query. So one thing we need to know is that, or need to mention again, is that only the where clause is accessing the base data. That's the vocabulary of the database. So suppose we pick the first bucket for first statement, and we use the where clause from the first view to rewrite this query, and we bring this up. And one thing we need to know is that we need to change the variable defined in the bucket in the where clause. And in addition to that, for those variables not defined in the bucket, we need to change it to a new variable in case the same view used many times to rewrite different query things. So we don't want this variable to clash. So we do this so on and so forth. For each candidate view, we take a bucket, and then we finish rewriting. Rewriting this query for generally one sample rewriting. Of course, there could be many rewritings for one query. Together we can calculate that this exponential blow up in the output because we need to build a condition for that. So one thing I want to mention is that we need to do a compatible check for the query results because we don't, which is not in this example because we don't want the same variable mapped to two different constants, which is not in this example but in the paper. So here's some remarks for the rewriting algorithm. The rewriting algorithm could result in exponential number of rewritings. And one intuitive question we want to ask is that can we do better? What if we translate everything to SQL and do rewriting in SQL? Well, we can prove the following results. Using the previous rewriting algorithm, the set of rewriting SPARQL query we generate is actually sound and complete. That said, there's no redundancy or misses result from the rewriting, and doing SQL rewriting won't help. It won't generate less rewritings as the current set of semantics is tight already. So experiment actually showed that SQL translation is indeed helpless. So, but still we want to do better. So this bring up the experiment optimization. And the first thing we do is that we try to minimize the size of a single query. Suppose we use the following bucket to rewrite the query. We'll find that the first two buckets are from the same view. They both use VF, and they join the same way in the query and the view. And we propose to merge this long partial rewriting by using one copy of the view VF using once. And we actually show that this could potentially lead to more efficient evaluation of the query, the rewriting query. And we also show that such optimization will not affect the soundness and completeness of the query. This could basically lead to the second result. The Q merge, resulting from replacing two copies of the same view by one copy, is equivalent to the original rewriting. The second optimization is to prune the query rewriting with empty results. Suppose we use the following two buckets to generate a rewriting. It basically asks for Ares friend of friend, who is also his relative. So basically, who are they? It turns out that Ares, the set of Ares friend of friend and his relative are disjoint. So it turns out that we can prune all the rewriting depending on these two buckets. Together, we can prune 1 times 1 times 2 times 4, 8 queries, 8 rewritings. So how do we implement this in the paper? Consider there's two triple patterns, Y1, P1, Y2, and Y3, P2, Y4. Suppose there's a join equals Y1 and Y3. And if we know the actual value set of Y1 and Y3 in the data set, then we can calculate the intersection. If the intersection is empty, then we can prune this join pattern. But indeed, in theory, a negative result is that Boolean intersection problem has been proven to require linear space. However, in practice, we can set it to a constant success probability and design space efficient heuristics. So instead of using the exact value set, we use the synopsis, denoted as alpha, AY1 and alpha AY3. So we use the synopsis to estimate the size of the joint, the size of the intersection. The size of the intersection in estimation is larger than the threshold. We continue with this rewriting. If not, we use the ask query. Remember, recall that ask query actually probe whether such join pattern exists in the database or not. If you return yes, then we continue. If not, then we can prune all the rewriting depending on this join pattern. So in the paper, we also present the heuristic how to avoid issuing excessive ask query in the rewriting. So in practice, we use k minimum value, KMV is enough to obtain unbiased explanation for the size of the job. In the paper, we also discuss how to maintain this analysis, like during updates. So here is some experimental results. We implement the rewriting algorithm and optimization with C++, and we define the query and views using benchmark data, LEBM. It's a data set about university domain, describing courses, students, and professors, and their email and phone information, and so on and so forth. And we generate 10 million tuples from LBM, and the platform we use is a 64-bit Linux machine with 2 gig Intel Xeon CPU and 4 gig memory. For the relational experiment, we do it on MySQL, and for the others, we evaluate on a for store, which is a generic RDF store. So we denote SPARQL query rewriting without optimization as SQR, and SPARQL query rewriting with optimization as OSQR, and we denote the SQL solution. Basically translate everything to SQL and do rewriting in relational database as SQL. And the full set of experiments in the paper. For the first set of experiment, we create 7 types of view for 14 persons respectively, and each of these views reflect partial personal information for that person. So each person released a portion of his 7 views for query, and for the first person, he published all his views. But for the last one, he only published the view about name. So we have a query that start with the first 3 property, and we incrementally asking for more until we reach 7 property. And so as this is the number of the query result from the experiment, as the number of the as the size of the query increase, so we can see that algorithm SQR, basically the naive rewriting, and SQL rewriting will end up with the same number of rewritings. This is indeed not surprising, because from the first result, we show that the naive rewriting has the same semantic in terms of number of query results as SQL. But on the other hand, algorithm OSQR, we can see that it results orders of magnitude less queries than the other 2 algorithms. This big difference we also carry on to the end-to-end evaluation time. You can see the algorithm OSQR result in orders of magnitude faster than the other 2 algorithms. And 2 minutes. Okay, probably I skip the second. So the result is basically the optimized algorithm can result in orders of magnitude faster than the other. So basically, here's the conclusion. We studied the rewriting query overviews in the context of SPARQL and RDF. We propose the first sound and complete rewriting algorithm with optimization to simplify individual writings and prune rewriting with empty results. Our solution is independent RDF store and has portable. So we we also use extensive experiment to demonstrate the method is efficient and scalable. So any questions?
I had a question. Before you were mentioning that when you're figuring out your candidate queries, you're trying to translate them. You obviously don't want the situation where they match the same variable. If you did have that situation, do you just remap, or is that actually a bigger problem?
It's not a problem, because we always map to a fresh.
Right.
Okay. So it never cache.
All right. Well, let's give our presenter a round of applause. Make sure you get your USB stick.